Welcome to This Explainer, where we are skipping all the fluff and diving straight into mastering banking security tokens for your Cambridge IGCSE Computer Science exam. Because, as you probably already know if you're studying syllabus 0478, just knowing the theory, yeah, it's not enough. You have to know exactly how the examiner wants you to apply it. So today, we're breaking down a complete micro-level learning unit right out of your textbook. We're going to focus entirely on how banking systems authenticate users, how they keep data safe, and, most importantly, how you can translate all of that knowledge into full marks on your paper. All right, take a look at this absolute trap of a question. Explain how a physical security token secures a banking transaction. That's a 4-mark question right there. Now, if you answer this with, generic terms like, it gives a secret code to keep hackers out, you are instantly going to lose grade boundaries. It is a massive, massive trap. Examiners, well, they aren't looking for a general understanding of security here. They want specific technical mechanisms tied directly to the scenario. So let's break down exactly how to avoid this really painful mistake and build an answer that examiners basically have to give full marks to. Section 1, Unlocking Authentication Methods. Okay, let's dive into this by first unpacking the technically precise authentication methods the Cambridge syllabus demands before we even get into network security. The first concept we need to look at is zero login. This is honestly such an ingenious method. It actually builds a behavioral profile of you across your devices so it can grant access without any traditional passwords. Think about your mobile device for a second. The software isn't just sitting there waiting for a password, it's actively detecting changes in your behavior. It checks when and where your logins occur, and it literally builds up a picture of your usage patterns. So, if your behavior matches the profile, boom, you're authenticated. But if the machine detects something unusual, it immediately triggers the system to lock the user out entirely. It's all this heavy security happening completely in the background. Next up, we have biometric authentication, which relies on undeniable physical traits to prove you are, in fact, the genuine account holder. The classic example you'll see in your textbook is a mobile device scanning a user's face to authenticate them. And because biological characteristics are just incredibly difficult to fake or duplicate, especially compared to, say, typing in a string of characters, biometrics offer a significantly higher baseline of security for sensitive stuff like banking. Now, this breakdown brilliantly illustrates the specific hardware differences you actually need to memorize to successfully tackle the activity on page 88 of your textbook. First, you've got the magnetic stripe, which you'll often find on the back of hotel door keys or older bank cards. That stores up to 60 characters of data magnetically, things like a name and account number, and it has to be swiped to be read. Smart cards, on the other hand, step up the security big time by using an embedded chip, which has obviously been standard in banking for years. But the absolute highest tier for our scenario is the physical token. This is a standalone hardware device used in conjunction with a synchronized key code. And guys, this specific hardware distinction is exactly what you need to highlight in your exams. Keep this in the back of your mind because in just a moment, I'm going to show you a hidden examiner clue that changes your answer completely. Missing it literally means dropping crucial marks. But to understand why that exact wording is so powerful, we really need to lay down the network theory first. We have to understand what actually happens to your data the second it leaves your computer. Section 2, Securing Data, HTTP versus HTTPS. Let's see how all this builds into the critical journey of your data once it leaves your device and travels across the internet. So when you're completing a banking transaction, you might have noticed a tiny padlock up in your browser, or seen that your address bar shifts from HTTP to HTTPS. Now, HTTP stands for Hypertext Transfer Protocol, and it's just the standard for data transfer. But for banking, it's dangerously unsecured. That is exactly why we need HTTPS, Secure Hypertext Transfer Protocol. That extra S at the end guarantees that a secure encrypted connection is made strictly between the two devices that are transferring data. And the absolute crucial point here is this. Data packets are encrypted before they are ever transmitted across the network, and they are decrypted only when they reach their intended destination. This is huge because it ensures that even if criminals, like hackers, manage to intercept your network traffic during the process, the data packets remain completely meaningless to them. Because the hacker lacks the specific decryption key, they are entirely unable to decipher the encryption. So that intercepted data, it's practically useless gibberish. But here's the thing, encryption isn't enough if the software itself is vulnerable. To maintain a watertight security environment, systems rely heavily on automating software updates. Why is this so important? Well, because operating systems are almost always released with security bugs in them. It happens simply because developers are often rushing to get the software out on sale. Automating updates ensures that developer patches are installed routinely to close up these hidden, dangerous security loopholes, and it removes the need to rely on the user to manually check for them. Basically, it patches the holes before the hackers can even find them. Section 3. Upgrading your exam answer. We've mastered the theory, so let's finally reveal that hidden examiner clue and systematically upgrade our exam technique. All right, here is the secret. Straight from Cambridge Exam Strategy, examiners will penalize you for using generic textbook definitions. You absolutely must map your knowledge to the specific scenario nouns and constraints in the prompt. For instance, if the scenario is about a bank, you need to talk about account numbers and financial interception. If it's about a physical token, you can't just call it a password generator. No way. You have to use the constraints of the scenario to frame your technical knowledge. So by rigidly applying this top-end answer framework, you can transform a fragile, guessing kind of answer into an undeniable full-mark response. It's 4 steps. First, state the concept clearly. Second, provide evidence or data directly from the scenario. Third, apply scientific or computational reasoning to explain how it works. And fourth, wrap it up using precise examiner wording. Let's actually see this framework in action and completely upgrade that trap question we looked at the beginning of our explainer. Now, what's really interesting here is seeing how a weak answer is instantly elevated just by injecting specific terms. A flawed answer might say something like, a token gives a secret code to log in securely so hackers can't get in. Honestly, that is a 0, maybe a 1-mark response. It's way too generic. But look at the upgrade. The physical token generates a synchronized key code. Bam, there's your precise hardware term. The user inputs this alongside their password. If a hacker intercepts the password, notice how we use the scenario noun intercepts right there? They still cannot access the bank account without possessing the physical token hardware. By using terms like synchronized key code, intercepts, and highlighting the actual physical hardware limitation, you've hit absolutely every mark on the rubric. Section 4. The next exam trap. You are now fully equipped to conquer banking security tokens, but this syllabus is filled with hidden landmines. Want to leave you with this final, really high-stakes question to ponder. If you don't know the exact difference between validation and verification data testing, how many marks are you risking on your next paper? Validation checks reasonableness, while verification checks that entered data is perfectly copied. But mixing up normal, abnormal, and boundary data testing, that is literally the #1 devastating mistake highlighted in the latest examiner reports. So how confident are you feeling about that? We'll solve this exact problem in our next explainer.